Hello. Yeah. Okay. Hello, everyone. Welcome to our first lecture of this course. So, since we are having many students from the embedded systems, and also it is going to be a revision for our ME micro students. So, in our first lecture, we will just get introduced to uh, the MOSFET model to be exact, the model which we will be primarily using for most of the circuit techniques which we are going to learn in this course. Okay. Of course, as you can see, this model is practically even less than half a page, if you can see this. Okay. So, I mean, obviously, this is a very, very simplistic model, but this is good enough for our basic purpose of the circuit perspective. Okay. Now, later on, towards the advanced stage of the course, I'm going to delve into the deeper aspects of the devices and technologies. So, whatever we are going to learn today concerning the device or the MOSFET IV characteristics, and later on we will do the CV characteristics also. So, the MOSFET IV and CV, what we are going to do right now at the very beginning of this course, are primarily for the microelectronics devices. Okay. So in our previous PMMD course, we have dealt with it in way more details than what we are going to study from the device aspect in this course. However, this is necessary for our understanding. So just a revision for the PMMD students and maybe a revision for the embedded system students also. So let's begin. So let us assume that we have got a semiconductor bar. Okay, so please note that whatever I'm going to tell you right now, this is far from complete. Okay, so this is just bare minimum which is necessary for designing circuits. All right, so let us assume that you have got a semiconductor bar, silicon bar. Okay, no devices as of now. Okay, now notice that if the cross section of the bar is A, okay, and then uh, this is a long kind of rectangular or cuboid kind of bar. So the cross section over here, I mean, the thickness over here is around dx, and small n happens to be the carrier density inside the semiconductor bar. These are actually the free carrier density. I am not going into so much of details. So small n is basically the number of electrons per unit volume. Please remember this. This is the unit of n is per centimeter cubed. Okay. So what is the number of carriers inside this dotted lines over here? Obviously, area multiplied by the length dx will give you the volume, and if you are multiplying by the n, which is the volume density or the density of the free carriers, that will essentially give you the number of carriers within the volume a dx. Cool. Okay, very simple. Small n, number of carriers per unit volume multiplied by the volume a into dx. Very nice. So therefore what we understand is that this n into a into dx number of electrons are actually moving through a distance of dx over here, okay, from here to there. All right, it is moving through a distance of dx centimeters, so that I'm putting centimeters, it's not necessary, you can put in meters, angstrom, whatever, but centimeters simply indicate the unit of time, the unit of space, unit of length, right? Then it is essentially moving a distance of dx in length scale in dt seconds. Seconds is the time scale. Okay, so what is the charge of which is moving through this cross section? I mean, a small strip. Obviously, the electron has a charge of minus q, isn't it? So I'm going to multiply minus q. Remember that minus q is the electron charge. electron is negatively charged. Everybody knows that. This is high school. Okay, so electron charge is minus q multiplied by the number of electrons which are moving. So minus q into n into a into dx. This much amount of charge will be moving through dx centimeters in dt seconds. Okay. Therefore, what is the rate of the charge flow? Remember, rate of the charge flow is how current is defined. Current is defined as the amount of charge flowing through any cross section in 1 second, right? So dx, so IN will be equal to this much amount of charge, that is minus q n a into dx divided by the time dt. Very simple. Okay. Now notice that dx by dt is nothing other than the velocity at which the electrons are moving. Correct? So if that velocity, we call it as the drift velocity. There are other transport phenomenon, diffusion, there are tunneling, there are many other things. I am not going into any of those details. You can, those of you who are interested, you can refer to your PMMD notes or the YouTube lectures on PMMD. Anyways, so dx by dt is the drift velocity VDR. All right. So remember, I'm carrying along with this minus q charge. This minus is still there. Okay. Now an interesting thing happens, that since area over here, a capital A, this area is kind of, it depends on the area of that semiconductor bar. So essentially meaning that this area factor is simply like a scaling factor for this entire expression, isn't it? So what we can do is, from a device perspective, it becomes easier if we consider something called current density. All right. So what is the current density? Simply the current IN divided by the cross-sectional area. As simple as that. Okay. So it simply turns out to be minus into q n into drift velocity VDR. Correct. Now, what is the expression for the drift velocity? Again, those of you who are interested, you can check out the PMMD lecture notes available on YouTube, as well as probably with your friends in the ME Micro. So this VDR, the drift velocity, is given by this relation. All these are done in PMMD. I'm just stating the result, because this has got nothing to do with this course, because this is primarily got to do with the material properties. Okay. So for circuits, we are mainly concerned about the IV and CV relations. Okay. So that's what we are aiming at right now. So the drift velocity is given by this relation. What is important for us to note is that notice that fx, x is what? X is this dimension, right? Is along this direction. That is x. I should rather put it in red color. Okay. So the field, if the field is along the x direction, then the drift velocity, I should actually put a vector sign over here, but for simplicity's sake, I'm not putting a vector, because remember, high school, fields, force, velocity, these are all vector quantities. Anyway, I'm not going into those complications right now. So if you consider those vector quantities, then what is interesting to note is, remember, if the field is in this direction, positive x direction, then where will the electrons flow? Electrons will always flow in the opposite direction. Okay. So if the direction of the field is in this direction, means what? This is the plus charge, this is the minus end. Correct. The electrons will flow from minus to the plus, right? So the direction of velocity, the direction of the electron velocity is exactly opposite to the direction of the field. Understood? So that is the reason why I put a minus sign over here. Okay. So those of you, if you ever try to do a PhD, okay, at the PhD interview, these are kind of the critical questions you can be asked. Okay, why are we putting a negative sign over here? For most of the job profiles which you'll be getting after the end of this semester, or within this course, or within this in bits mostly. Okay, those job profiles usually don't go into that much details, but later on, after few years, if you feel like you want to go into industrial R&D sector, okay, you will never get into R&D profile in bits after the ME micro or ME embedded, right? So if you ever want to go into industrial R&D, or you want to go in for a PhD, R&D will require a PhD degree anyways. All these intricate details are necessary. Okay, so the negative is because of the thing that the velocity, direction of the electron velocity is exactly equal and opposite to the direction of the applied electric field. Okay, and that has got to do with the negative charge of the electron, minus q, as I have shown over here. All right, so now comes a very, very important thing, again necessary for your R&D kind of profile. Everywhere you will notice that drift velocity is written as proportional to the field. Again, in the PMMD course, we have dealt with it in a lot of details. All the theory that you learn, okay, whether it is PMMD or VLSI design or advanced VLSI design, they are all based on the first premise that these are all based on the low field approximation. What is the meaning of that? That means no matter what happens inside the MOSFET, I will not speak about any other devices. So inside the MOSFET device, what will happen? The fields inside the device are almost invariably much lower than the critical field FC of that particular material used. Okay, so this critical field FC is a parameter for that particular material, not the device. Okay, remember, the device is actually made of what material? Silicon, right? Whether it is doped with N-type, P-type, all those things we will see later. This is N plus, silicon. The semiconductor bar, silicon. Everywhere it is silicon, okay? So if it is silicon, then that silicon material will have a particular value of the critical field. Okay, so this critical field, again, I discussed it in PMMD, just to recall. So if this is your drift velocity and this is your field, then there is a particular value of the critical field over here. Let me call it FC, beyond which the drift velocity becomes flat. And less than FC, it is going to be proportional to the field F. In fact, so I'll put here Fx commensurate with the axis which I have drawn in these two diagrams. Okay, so now what happens is, if it is a low field situation, low field means low with respect to what? Again, interview question for PhD. Low fields means low field with respect to the critical field of the material used. So if you are, I don't know why will you do it, but suppose you make the MOSFET with gallium arsenide, then gallium arsenide is going to have a different critical field than silicon. Okay, but remember, this these approximations of low field analysis and all that, they break down in ballistic transport and modern like 5 nanometer technology nodes. So as I said, the discussion which we are doing is in the micron technology. Okay, very basics. Okay, so in fact, the diagram which I have shown over here concerning the drift velocity relation with respect to the field, this has got serious implications on the device and circuit parlance. So we will discuss this as we go along. So as of now, you should be happy that for low fields, and by the way, why will it always be low field? Because we are talking about micron technology. That means the distance between the source and the drain regions of the MOSFET. So this is the internal structure of a MOSFET. I have simply cut open the gate which is above the channel region. Okay, so this is the inner diagram, let us say. So those of you who are still in the, so the gate will be something like this above. Okay, so if the channel length is L, as you can see from the distance between the source and the drain is capital L, then for the micron technology, okay, large devices, then this capital L will be in the order of, I mean, close to 500 nanometers or so or higher, okay. In those kind of devices, obviously the distance between the drain and the source is so large, as a consequence, the field will always be low, okay. So if the, because the fields are given by, so Fx is equal to VDS divided by the channel length. So if L is large, the field is low. Correct? Now the question you might ask is, sir, I can of course put VDS also very large. The thing is that for every technology node, you will notice that there is always a limitation on how much maximum power power supply you can apply. For example, in this course, we will be dealing with 45 nanometers technology. So in 45 nanometer technology, VDS, maximum VDS, so if I can write it like this, so VDS max will be the VDD, correct? So this VDD power supply happens to be 1 volt for 45 nanometer. So in your VLSI design course, you have done with 180 nanometers, correct? 180 nanometers में कितना था? Can anybody tell me? Hello.
1.8.
1.8.
Excellent, excellent, very good. So that means now you can realize why are we imposing this 1.8. So why can't you apply 4.8 in case of 180 nanometers? Because this low field approximation will not hold. Got it? So if you're increasing this instead of 1.8 in 180 nanometers only, if you're doing it 4.8 or something, then VDS is so high, then this FX will not be in the low field region. So the entire device theory, the entire circuit theory, the entire circuit will not work. Okay. So again, as I said, this is a very, very critical understanding here. In fact, throughout the course, I'll be teaching you with this tips for your interviews. So for R&D level interviews, this is one of the things. So in the interview, people can ask you, what is the fundamental assumption for your entire, all the models, circuit models, device models, the inverter models, the i7 models, whatever models you want, whatever circuit designs you are making, this is one of the things to be kept in mind. It is all built, designed for low fields. Okay, very good. So if it is under low field, if you clearly understand that Fx is much lower than Fc, so we can simply ignore this, and therefore drift velocity simply becomes minus mu(n) into Fx. Very nice, isn't it? So all I'm going to do is I'll just put this minus mu(n) into Fx right here. Okay, so from this step to this step, under low fields, we will get a plus over here because this is also a minus, this is also a minus. This minus was because of the electronic charge, which is negative. This minus is because of, we have already seen, the direction of the drift velocity is opposite to the direction of the field. That is coming from the vector signs. Okay, very good. So throughout the entire course, lot of concepts will become clear. Okay, so just bear with me. And unlike many courses probably which you have done, this course is not about memorizing a few formulas and basically solving a few problems based on those equations or formulas. Here it will be more about concept building so that you can design the circuits. Okay, very nice. So once you have put this minus mu(n) Fx over here instead of this VDR, you are going to have plus Qn mu(n) into the field. I'll put Fx here because we are referring to only the lateral field. Okay, the vertical field has got immense importance, but for those I'll skip for this course. If you are interested, please refer to the PMMD lectures. Okay. So once you have got this Q in mu n, that is written as conductivity. Okay. Conductivity is equal to NQ mu n. Okay. There are also other parts for the holes. We don't need to bother about the holes because, can anybody tell me why am I not writing PQ mu P here? This part is missing. At least the ME micro students should be able to tell me. In PMMD, yes, please tell me.
In the inversion, like minority carriers.
Okay, the main reason is that in case of MOSFETs are what? Unipolar device. Okay, so that means if I am making an N MOSFET, which I have shown over here, it will be only electrons. The holes are not there. Okay. Minority carriers, yes. So if you are speaking about minority carriers in the P MOSFET, then you are going to replace N by P and mu P, Fx and everything. Okay. But however, if you are speaking about a diode or a BJT, which of course, as I said, we are going to skip the entire part of diode BJT, that's simply obsolete. Now, in BJT and diodes, it is a bipolar device. So you are going to have the holes as well. So I'm going to put the P, Q, mu, P. So this is one aspect of MOSFET which is actually good. Okay, you don't have to bother about the holes. I mean, it is only either electrons or holes. Okay, very good. So this is the definition of the conductivity. I'll put 3 here because this is a definition. That means equivalent. Okay, now comes a very interesting part. What we are going to observe that, remember I told you about the vertical field, the field along the y direction. So that field, vertical field, will be important for creation of the inversion layer. Okay. Now the creation of the inversion layer had taken a lot of analysis in the PMMD course. Those of you who are interested, revise that. In this course, we are not going to go into the creation of the inversion layer or the creation of the channel. So obviously, because if it is before the channel is formed, the device will be operating in the subthreshold region. Okay, by the way, please note, in VLSI design or in your BTech or in the previous courses, in many other courses, the professors will be telling that when VGS is less than VT, that means device is switched off. No, no, no. Device is in the submicron device, submicron operation. This is sub-VT operation. We will do sub-VT circuit designs in this course. Your smartphones will operate only if it is mostly, I mean, many circuits are there in your smartphone which operate in the sub-VT. That means the VGS is less than VT. So if VGS less than VT is device is off only, okay, you simply cannot get smartphones in modern technology. Okay, so that is a wrong concept that VGS less than VT the device is switched off. No, VGS less than VT device is in subthreshold operation. Okay, so in the submicron and in the special, not even submicron, let us say 45 nanometer, 10 nanometer technology node, in the nanometer scale. Okay, when the devices are in the nanoscale devices of, you have subthreshold operation. So that you have to keep in mind. Okay, so we will assume that the VGS is greater than VT for this micron device, huge micron device. Then we will try to find out what is the total inversion charge in the channel. Okay, कैसे निकालेंगे? This is a revision for the PMMD students. So notice that the minimum amount of charge necessary to have this channel is the VGS minus the threshold voltage. So remember, the vertical field, the field along the y direction, that will give you MOS capacitors and all those things. which will essentially lead to the definition of this very, very important parameter called threshold voltage. In this course, which is mainly on circuits, we will not bother about how to get this VT. How to design the VT is the part of the PMMD. Okay, the device engineers will design the VT. So, for example, all of you have been using 180 nanometer technology node, right? One day we will open up a technology file and we will meticulously see what is written inside that library. What we are doing right now in the cadence, we are simply thinking that God has given us the libraries, and with that God gifted library, we are basically designing the circuits, right? Remember, God has given us the brain. Okay, the libraries, we used our brains to develop these libraries. So this VT is actually provided in the library. Okay, so whenever you are designing using 180 nanometer or 45 nanometer, the VT is provided accordingly. Okay, so so basically when you are designing circuits, the VT is already known to you based on the library file. Okay, in this course I will provide you with the threshold voltage, and accordingly you will make the devices, you will make the circuits and all that. Okay, very good. So VT is provided. Excellent. Now VT provided matlab the device is already in the linear or saturation region. Submicron mein nahi hai, the device is already switched on. Okay, so inversion charge will appear when it is already switched on. VGS is greater than VT. So inversion charge will be obviously capacitance multiplied by the voltage. The voltage to yahan hai, VGS minus VT. So this happens to be the minimum charge for inversion. But there is a minus here. Who can tell me why it is minus? Why have we put a minus here? Hello?
Electron.
Better answers, please. From the circuits perspective, think like a circuits designer here, not a device engineer. Circuit engineer, IC designer. बोलो माइनस क्यों है? PMMD guys, come on. We worked on this for the whole semester.
So from the net charge equation.
What is the voltage you are applying here? Positive or negative?
Positive.
Positive. Why? Because this is actually an N MOSFET, like N plus, right? So this is P silicon. This is actually P silicon here. This is N plus, N plus. This is like an isometric view. This is the cross-sectional view anyway. So now if you're making an inversion layer, so that means the inversion layer will be spread out here. This inversion layer means full of electrons. Okay. Now notice that if you are applying a positive VGS, whether it is electrons going inside the device, you will find electrons will be there. That is the inversion charge, and the depletion charge will also be there. I am not going into whether it is electron charge or depletion charge or ionic charge or whatever. Let's not bother about it. There will be even some defects also in the oxide that will lead to interface trap charges. Embedded system students, please don't get scared. I'm just explaining to the little bit to the, I'm just kind of revising for the PMMD guys. Okay? These remember what are these? These are the interface trap charges, QIT. That will affect the VT. So in this course, since we already have the VT with us, you don't have to bother about this QIT and all that stuff. So as a circuit designer, your answer should be, why it is negative? The answer is very simple. You are applying a plus VGS here. So that means the gate terminal will be plus charges. So inside the semiconductor, it is always going to be negative charges, because it is basically plus charge minus charge. It is nothing more than a capacitor. Okay, remember MOSFET is actually basically a capacitor. Okay, तो दैट मीन्स यहाँ पर अगर आप प्लस VG दे रहे हो तो गेट टर्मिनल में क्या होगा, गेट टर्मिनल इज मेटल राइट, तो मेटल में आप पॉजिटिव चार्जेस दे रहे हो, तो सेमीकंडक्टर में क्या होना है, नेगेटिव चार्जेस होने हैं ना, सो दैट इक्वल एंड ऑपोजिट नेगेटिव चार्जेस. नाउ इन द प्रीलिमिनरी कोर्स वी वेंट डीपर इनटू इट, वी फाइंड आउट how much fraction of this negative charge will be the inversion charge, how much fraction will be the depletion charge, how much fraction will be the interface trap charge. All those things are not necessary in this course. Okay, but this will be necessary for you to, but this will be necessary for the device people to keep in mind. Okay, again these will be necessary if you are trying to pursue PhD later on. Okay, so now we have understood the reason why we have got a negative over here, minus. ठीक है, because inversion charge, depletion charge, जो भी semiconductor में जो भी charge है, जैसे कि जो मैंने यहाँ पर draw किया है, whatever I have drawn over here, this is nothing other than the silicon. So whatever charges you see, whether it is the charge in the channel, inversion charge, या depletion charge, whatever charge, they are all negative because you are applying positive charge on the terminal. तो कैपेसिटर हो गई एक. सो दिस इज योर सिलिकॉन पार्ट, दिस इज द मेटल पार्ट. इसीलिए तो MOS कहते हैं, मेटल ऑक्साइड सेमीकंडक्टर फील्ड इफेक्ट ट्रांजिस्टर, दैट इज द फुल फॉर्म ऑफ अ MOSFET. तो यहां पर अगर आप प्लस VG दोगे तो दिस इज ऑलवेज गोइंग टू बी प्लस राइट. तो यहां पर व्हाटएवर इट इज, व्हाटएवर इन्वर्शन चार्ज, कुछ भी चार्ज हो, सारे के सारे चार्जेस नेगेटिव होने ही हैं, कंपल्सरी. Otherwise, this is not a capacitor. Excellent. Awesome. So this is the minimum charge necessary for the inversion is minus COX into VGS minus VT. और यहाँ पर हमने क्या किया है? Simply Q is equal to C into V. High school. This is not engineering also. High school. तो high school में सीखे थे ना? Capacitor into voltage is equal to the charge. Okay. Okay, since I am unable to see Ashok,
Yes, sir. Yes, sir.
Just open up your microphone and just speak up. Yeah.
Yes, sir. Am I audible?
Yeah.
Sir, even if we apply negative gate voltage, the equation will be this only, right? I mean,
No. If you are applying a negative gate voltage to the N MOSFET, what will happen? There will be no question of inversion only. Inversion कब हो रहा है? When you are as let me just put Control Z. Okay. Just see. Okay, this is a typical case where you have applied a plus VGS over here. Okay, then if you are applying a positive one only, then first thing will be you are depleting this part and then you are bringing in the electrons. Then we call it as an inversion. Why inversion? Because the channel originally was p-type. This was p-type material, right? Now because of so much of VGS which is greater than VT, N for N MOSFET, VT, the electrons have come to the surface. So what is happening? Then you are making the surface as much N-type as the bulk is p-type, remember? But the problem is, what Ashok is telling is if you are applying a minus VG, obviously this is going to be less. Okay, then what will happen? You are not going to do any depletion there. You are going to have more number of holes on the surface. Then what is the situation? You are applying a negative charge and you are having a plus over here. So this kind of operation is called accumulation mode MOSFET. So in this case, you will not have the concept of VT alone. So that means if you want to switch on the device, this is your VGS, this is your ID. Your MOSFET will always be switched on here because there is no concept of threshold voltage itself. So how are you going to use this MOSFET, accumulation mode MOSFET, for your digital applications? Correct? Yes. In digital applications, what you have to do? If the VGS is less than VT, the device is in subthreshold region, current is very low. That means we will call it as zero logic. The moment VGS is higher than VT, so the VT का concept ही नहीं रहेगा. Very good. Thank you, Ashok.
Yes, sir. Actually, as you said, when we apply positive voltage at VGS
Correct.
and all, so irrespective of VGS, the equation remains same, right?
I
mean, sir, if VGS is negative, Q
This
inversion
equation will
becomes positive.
remain same in the sense like your VTN will not be there in that case.
Yes, sir. I mean, the equation formulated from the equation VGB equal to VFB plus Vox, like that.
Yeah, that will remain. This will always be remaining the same.
Yeah, yes, sir. Yes, sir.
Okay. The only thing is that this VTN concept will not be there.
Okay, sir.
Correct. Because charge is equal to capacitance into voltage is the fundamental electromagnetics formula. Okay.
Yes, sir.
Excellent. So now what we will do is, now notice the channel region. Okay. Embedded students, is it okay? Hello? Anyone from the embedded group? See, this is the, I'm just spending one class, one lecture on the MOSFET basics so that you will not be thrown out of balance when we are going into the tremendous amount of circuits later on. Anybody from embedded? Are you still with me?
Yes, sir.
Yeah, thank you so much. Okay, so now this is the minimum charge necessary for the inversion. Okay, now what is interesting is the fact that now in the case of a MOSFET, what we usually do is we are going to connect the source side to the ground and we will connect the drain side to plus VDD. Let us simply call plus VDS because the source is grounded. Okay, so notice you are applying a plus VDS positive voltage to the N plus region. Correct? So that means this N plus and P junction is what? Reverse bias, forward bias? Reverse biased, right? As a consequence, the thickness of the channel or the thickness of the inversion layer, we shouldn't call it thickness. Technically, it is basically the carrier concentration, but I'm not going into those details. So the thickness of the inversion layer will keep on decreasing as we go from the source to the drain. But what we have understood that the minimum charge necessary for inversion is already this. Okay. So we can say that let us assume that this channel is gradually decreasing. This is called the gradual channel approximation. Okay. Gradual channel approximation. ठीक है ना? Only Texas Instruments or Intel or these kind of companies can ask you such in-depth questions, but mostly not. Okay, so GCA is this gradual channel. That means this is actually linear variation. अगर ये linear variation है, then we can put the voltage along the channel is also V into it. V as a function of X. Correct? It is decreasing as this. So अगर हम x equal to 0 ले लेते हैं ना, तो वहां पर this potential the F is 0, Vx is 0. Why? Because you have put it as a ground, dear. यहाँ तो ground है ना, तो यहाँ पर potential at x equal to 0 at the source terminal will be 0. That means it will be simply minus COX into VOV. Now VOV is basically VGS minus VT. Overdrive, gate overdrive. So what is the inversion charge on the drain end? It will be minus COX VOV, VGS minus VT. और ये VX क्या होगा यहाँ पर? VDS voltage है ना? यहाँ पर 0 है because it is ground. यहाँ पर VDS है because you have applied VDS here. Very simple. तो अगर हम यहाँ पर GCA लेते हैं ना, now something interesting is there. Notice that this is what? ये वाला shape है. ये क्या है? You can tell me.
Trapezium.
Yes, exactly. This is actually a trapezium. इसको अगर हम 3D बना देते हैं, क्या हो जाएगा? Trapezoid. Very good. Okay, तो ये तो trapezoid ही तो है ना? देखो, दिख रहा है? हाँ, this is basically the trapezoid. So if it is a trapezoid, then what we are going to do now, हमें अभी टोटल इन्वर्शन चार्ज निकालेंगे. ठीक है, टोटल इन्वर्शन चार्ज क्या होगा? वॉल्यूम इनसाइड द ट्रेपेजॉइड. पहले ट्रेपेजियम का निकालते हैं, ये वाला फर्स्ट फेस. क्या है ये? This is, if this is the base, this is H1, this is H2. What is the area of the trapezium? कौन बताएगा? This one only, right? Huh? Everybody say. This is not even high school. This is, I think, secondary school, class 8. ठीक है? I am showing it through basic school level geometry. Very good. So half. What is the base over here? कोई तो बताओ यार. Channel length L. Very good. H1 plus H2. H1 क्या है? The charge on the x equal to 0. H2 क्या है? Charge on x equal to capital L. तो वही मैंने बिठाया है. Okay, this is the base over here. अब ये trapezoid हम निकालेंगे, right? So trapezoid माने there will be this thickness also. What is the thickness here? Obviously the width W. Very simple, right? So देखो, so now what we are getting is, माइनस बाहर निकालो, W इंटू L इंटू सी ऑक्स बाहर निकालो. आपके पास यहाँ पर क्या हो जाएगा? ट्वाइस VOV माइनस VDS. ओके, तो what you can do is, since this 2 is here, तो माइनस WL सी ऑक्स VOV माइनस VDS by 2. ठीक है, अभी हमें करंट निकालना है. हम चार्ज देके क्या करेंगे? हम तो सर्किट डिजाइनर्स हैं. ओके, तो current, net current will be given by, simply I'll put a equivalent sign because this is equal to by definition. That means Q inversion, ये total जो जितना charge है, divided by the time taken for the electrons to move from the source to the drain. How much will be the time taken for the electrons to move from the source to the drain? Very simple. Total channel length divided by the drift velocity. Okay, वही तो किए हैं, L divided by VDR. अब VDR हमने आराम से पहले निकाल के रखे हैं, माइनस म्यू एन इंटू एफ एक्स. ठीक है, तो वही हम इधर डालेंगे. फर्स्ट ऑफ ऑल क्यू इन्वर्जन का तो हमारे पास है ही. So all I'm going to do is I'll put this equation over here, minus WL Cox VOB minus VDS by 2, as we'll replace this Q inversion. Remember, there is a negative. Cool. This L is initially there, LL cancels. Fine. How about the VDR? I'll copy from here, minus mu n into fx. Now we are happy. This minus and minus will cancel. Okay. Now you will be having mu n W Cox VOV minus VDS by 2, और यहाँ पर fx जो था ना, fx क्या था? fx was the field along the x direction. fx I have told you, it is nothing but the VDS voltage. देखो, drain side में voltage VDS है, source side में voltage 0 है, because it is grounded. So VDS is the voltage between the source and the drain, divided by the channel length L. So voltage divided by channel length is basically the field, VDS by L. तो आपका क्या हो जाएगा? This L, if you bring it in front, mu n Cox by 2. I have brought this 2 outside, huh? W by L this. So this whole factor, half mu n Cox W by L को हम बीटा कहते हैं. Very simple. So in device level designs, as a device engineer, you have to bother about this beta a lot. As a circuit engineer, beta will mostly be provided in the technology node, or it will be provided by the device people. Okay, so यहाँ पर beta हो गया, which is you will take considered as constant, twice VOV minus VDS into VDS. Okay, Now we will do something very interesting. So this is essentially the IV relation of the MOSFET. Okay, तो इसका characteristics निकालेंगे कैसे? Okay, so what I have done here is this. Notice this relation beta twice VOV minus VDS into VDS. I wrote a very simple Python code over here on the right hand side. My favorite editor is Visual Studio, VS Code. Anyway, so I have written this. What we will do is, I am not going into this models and all. This program was given as a as an assignment in the PMMD. Once we run this, I have taken the beta over here as 1 milliampere per volt square. Okay, so VT I have chosen as 0.5. These are randomly chosen values. As I said, beta and VT will be provided by the device people. So now, if you notice that this is the typical characteristics which you have seen. I have simply developed the model from scratch, and then I simply coded the model in Python and basically plotted it here. Okay, very simple. Now, what is important as a circuit designer is not this. What is important is, where is the region of operation of the MOSFET? Okay, so notice that if I just do this, for different values of VGS, if you will notice that when VGS equal to 0.5, this is ID VDS curve. Okay, when VGS equal to 0.5, then given that VT equal to 0.5, then VGS equal to 0.5, ID is equal to 0. Is it 0? It's actually not 0. It is 0 in the microampere scale. We will look into it in the submicron design later on. If I plot this in the semi-log plot, then you are going to have a whole new world inside this 0. We will look into that later. Okay, so when VGS is equal to 0.5 and going up, what is important is, notice these dots over here. If you notice this, after this dot, this is becoming flat. Okay, so these dots are essentially the boundaries between two different variation of the operation. So all of you must be knowing it. Like beyond this dot, it is the saturation region. Less than this dot is the linear region. We assume that it is linear. Of course, this is not linear, but I mean, the PMMD students know that this is called moderate inversion region. But anyways, we will not go into those details here. Now, the question is, what is the value of these dots? All of you have done VLSI design. Please tell me, what is the value of these dots? What value in the sense, like what are the coordinates of these dots?
VGS minus VT, sir.
VGS
minus VT.
So VDS equal to VGS minus VT, right?
Yes, sir.
Correct. So now if you notice, I have simply written two functions over here. These are the two functions which I have developed over here. Beta into twice, you can see this. I have just written the functions over here, saturation region and linear region. Okay. Now, since we are plotting VDS over here, these will be VGS minus VT, as your friend has rightly said. Okay. Now the thing is, if we are, okay, let's do one thing. I'll just take a screenshot of this. Just a second. Right, this is one, the other one is coming up. Now this is the IDVGS plot. Okay. Now who can tell me where are the linear saturation boundary over here? What are the values of the linear saturation boundary in the IDVGS plot?
VDS plus VT.
VDS plus VT, excellent. So what we are going to do here is, if you notice that I have simply plotted like that, plus VT, I have simply added this value of VDS over here. So once I plot it, it's exactly matching the linear saturation boundaries. Okay, so here also I'll take a screenshot. Nice. Okay, अब मेरा Python का काम हो गया. No need to bother about it. So these are essentially, I'm not drawing by hand. I have got from exact models itself. I have used Python for doing it, the exact values. I could have used MATLAB, but I always prefer Python. Okay. So now, if we draw this curve here, and here, if you will notice that this exact parabola which you see, if you simply transfer it over here, if you simply transfer this parabola, ठीक है, एक काम करते हैं, कर ही डालते हैं, Control C, Control V. So this was the parabola, right? इसको हम इधर शिफ्ट कर रहे हैं. Amazing, right? Did we? I do not think anybody studied MOSFET like this. So what is interesting for us to note is that when you are plotting the IDVGS curve, when you are plotting the IDVGS curve, when you are getting the maximum current जिस curve में होगा, that is exactly going to match the linear saturation boundary in the IDVGS plot, as you can see. Everyone clear? Dekho, I have just. So what is the meaning of that? That means, and by the way, when we say that यहाँ पर तो clear है. So in this case, it is very, very clear for all of us. So this is linear, this is the saturation. In this case, what is the linear and saturation region? In the case of IDVGS? Tell me. This is very interesting.
Sir, first saturation, then linear.
First होगा 0 to 0.5 तक क्या है?
Cutoff or sub VT?
Sub threshold.
Don't say cutoff anymore. Sub threshold. Very good. We will call it sub VT. Okay. So after that, what is the next region?
Saturation.
Very nice. Saturation कहाँ से आ रहा है? कहाँ तक?
VDS plus VT.
Absolutely, which are indicated by these dotted lines. So that means, notice, for take any particular value of VDS. Let us say VDS ये 150 वाला. That means this red color. Red color is this one, right? Sorry. So this is your VDS equal to 150 millivolt. Yeah, red, this one. Okay. So I'm just choosing any random one in the middle. So if this is the red one, so VDS plus VT will be given by this red dot over here. Okay. So that means this is going to be your VDS plus VT. Okay. Now this VDS plus VT, this VDS will keep on changing with the value of whichever characteristics you are choosing. Okay? So if you're speaking about, let us say, this green, what is this green? Let's take the orange. Okay, what is this orange? This is 50 millivolt. Obviously, this is going to come until here. This is the orange dot, correct? I hope you can see it. So this is your VDS plus VT for that orange line. I am using the same color pen. Okay. So when you are increasing your VDS value, VGS value, sorry, first will be subthreshold until VGS equal to VT. After that, what is the region of your saturation will depend on the value of VDS. That is what I'm trying to tell you. So if the VDS is less, the saturation region is less. If the VDS is more, the saturation region is more, because it is VDS plus VT. Understood? Then what is interesting is that, so all we know, you have always seen, all of you know that this is a saturation region. Excellent. इसको हम linear कहते हैं. क्यों linear कहते हैं? Because now you can see that the red one, for example, beyond VDS plus VT, ये क्या है? This is a straight line only, right? So beyond this VDS plus VT, this is becoming linear, yani straight line. Before this linearity begins, these dotted जो dots लगाए हैं, उसके पहले, this is basically the same parabola which we drew over here. Okay, so what do we understand in the IDVG plot? Before VT, it is subthreshold. It is actually exponential variation. PMMD students know it. I will explain that in this course also, but a little bit, not much. So in the subthreshold region, it is actually exponential. We cannot see it in the linear scale over here. This is the linear plot, not log scale. In the log scale, you will be able to see a lot of variation in this subthreshold region. Anyway, so beyond this VT, which is VT is equal to 0.5, remember, in all these diagrams. So if VT is 0.5, uske baad se, it is actually traversing the same parabolic relation which we have here until it reaches the point VDS plus VT, which is the linear saturation boundary. Uske baad, ये straight line हो जा रहा है. All of them, if you see this brown dot and this brown becomes straight line. Brown is basically 250 millivolts. Got it, everyone? Huh? Excellent. In the next class, we will begin with the understanding of these characteristics, and then we will proceed for the circuit operations of the MOSFETs. Okay, that's all for today. Thank you so much.